Now it's time for College Algebra, Section 6.6 on polynomial and rational inequalities. So the difference, we're not just solving an equation, we're solving an inequality. So we're going to look at polynomials and rational. We've already solved both of those in previous lessons. So if you need to review how to solve an equation, you'll want to go look back at those other lessons. It's all in Chapter 6 here. But now we're going to focus on inequalities. So the difference with an inequality is not just looking for where it equals, it's going to be between some numbers. So I need to figure out what those boundaries are. So that's the first step. Basically, turn your equation, get it equal to 0 and solve it. I would just say step 1, solve it. Just like the last lessons, pretend like that's an equal sign, solve the equation. We need to know where those breaking points are, where they're equal to 0. And then you also have to, like for rational ones, you have to pay attention to the denominator. But for polynomials, you just solve it. And then we just have to decide if it's in which numbers it is true in between. So we make something called a sign chart or a sign diagram. So I'm going to show you how to do that if you haven't done it before. I believe we did it with quadratics earlier in the year. And then you just need to write your answer out. You can write it either in interval notation or with inequalities. I'll show you both ways. So for the first polynomial here, we just have an application. So this helps you put the answers into reasonable context. But if you didn't even have the context and you had this polynomial, we could still solve it. So we have this 12 by 12 box with the corners cut off. I've seen problems like this before. They've already written the volume function out for us. And we want to solve it. So use factoring and then find the values of x that give positive values for v of x. So we want to know when this volume will be positive because we obviously don't want a negative volume. So we've got this over on the next page ready to go. So it said use factoring to solve this. Basically, I'm just going to treat this like it's equal to 0 right now and factor. So what do all of these have in common? They all have a 4 and they all have an x. So I'm going to factor out 4x, and I'm going to start with the highest one because I want these in descending order. So if I divide 4x out of this, I'm going to be left with x squared. If I divide 4x out of this, I'm going to be left with 12x. And then if I divide 144 divided by 4, I get 36. So that's going to be plus 36. And like I said, for now, I'm just going to treat this like equal to 0, and we'll figure that out in a minute. So let's keep factoring. We're going to take x squared minus 12x plus 36. Well, that's x minus 6, and x minus 6 multiplied by 36 and adds up to negative 12. So the zero product property says that 4x equals 0. Divide by 4. So my answers are 0. Or these both tell me the answer is 6. So we seek those values of x that give positive values for volume. So 0 and 6 have something to do with this. The question is, where would I have a positive volume? So these would be where it equals 0. This is where volume would be equal to 0. And I don't want them equal to 0. I want them greater than 0. So now we're going to do this little thing called a sign chart. Here's my sign chart. Put the numbers you got on here, 0 and 6. And those are not solutions because they equal 0. And I want them to be greater than 0. So if you plug in 0 into this equation up here, you get 0 is greater than 0, which is false. If you plug in a 6, you get 0 greater than 0, which is false. So what we want to know now is where is this true? So if you plug in a negative, any negative number, you can plug in a negative 1 or anything. What do you get? So you can take the time, type that in your calculator with a negative 1 real quick. Guess what? You get a negative answer. So it's greater than 0 is false. This is not a true space. Now if I plug in, let's say a 1, I would get 144 minus 48 times 1 plus 4 times 1. I would get 100. Is 100 greater than 0? Yes. So in this section, I do have positive volumes. What about bigger than 6? Pick a big number like 10 or something. 144 times 10 plus 48 times 100. Oh, that was a minus, sorry. I'm doing it in my calculator right now. Plus 4 times 1,000 is 640. So over here, this is definitely true as well. And my calculator is not letting me write that. So here we go. Nope. True. Okay. So where is my answer? This is the last step. You got to make your sign chart, but then you got to tell me what the actual answer is. Where does this have positive volume? It has positive volume. I'm going to do interval notation first, not including 0, but from 0 to 6, and also from 6 on up to infinity. And we just put a U in here to union those two sets. I can't just go from 0 to infinity because 6 is not included. So you got to name this little interval and this interval. If I do that with inequalities, this means that 0 is less than x is less than 6. X is stuck in between 0 and 6. Or x is greater than 6. So I'm in this section or I'm in this section. That's in inequality or set notation, and that's interval notation. So that's the answer they're looking for part A. For part B, which value would actually give me a box? Now, since this is a real world problem, if I have 12 and I cut off bigger than 6, then I'm not even going to have a box. So for the part B, what answers actually would make a box would just be between 0 and 6. So my x value that I cut off of these corners right here can't be bigger than 6. It has to be between 0 and 6. And that would give me a positive volume. And that's all they asked for on this question. So moving on to rational inequalities. Rational inequalities are exactly the same. You're going to solve them and find those solution points. The other thing you also have to do is check for where the vertical asymptote is. Where the vertical asymptote is also going to be a point where it could flip and change from positive to negative. So you have to check for that as well. And that's the only extra step. So I'll show you a problem here real quick. Here's my cost problem again. And so number one step is I want to find the number of televisions that must be produced to keep an average cost at most $5.90 per TV. So I'm going to put my $5.90 over here and solve this equation. So here we go. I want to keep it at most $5.90, so that means less than or equal to. As I'm solving it, I'm just going to pretend like this is an equal sign because it makes the solving part equal or a little bit easier. All right, so my common denominator is x. I'm going to multiply both sides by x. Over here, that's going to cancel it out completely. So I have 5,000 plus 80x plus x squared equals 590x. I got to get these together on one side. And I also want to write them in descending order. So I'm going to start with x squared. And then 80 minus 590 is negative 510. X plus 5,000 equals 0. Okay, so 5,000 and 510. What do you think? Can you find any factors that might multiply to be 5,000 and have to do with 510? That was a big hint there. 500 times 10 is 5,000. So this is x minus 500, x minus 10. Now that one might have taken you a little while to get. If you're stuck on something like that, you could always graph this and try to find where the zeros are, the x-intercepts, and try to solve it that way. So if you're stuck on factoring, you can use other tools to help you. They kept the numbers kind of nice on that one. Anyway, so this is my rational function. So the values where it would equal exactly 590 is at 10 and 500, but the question isn't where does it equal. It finds we want to keep it at most 590, so we actually want to keep it under that. So let's take our values and our asymptote. What is the vertical asymptote of this graph? The bottom cannot equal 0, so there's also a vertical asymptote at 0. So I'm going to take all three of these values and put them on a sign chart. So here we go, 0, 10, and 500. Just random sign chart. It doesn't have to be to scale or anything. Just put a number line with those three numbers on it, and now we're going to test values. We know it's It said less than or equal to, right? So we know it equals 590 at 10 and at 500. And at 0, that's an asymptote, so it does not equal anything. We can't plug 0 in. So that's an open dot, and then these two get to closed dots. So we can start with that. Now, pick numbers in between all these things to check. Are we ever going to have negative? We can start with that. Are you going to have a negative number of TVs? No. So for this problem, we don't even need to check over here. That's fine. Between 0 and 10. So pick a number between 0 and 10. I like to use 1 because it's nice and easy. And plug in a 1. And you get 5,000 plus 80 plus 1. And is that less than or equal to 590? No, it's a huge number. So this area right here is false. I like to put false. Pick a number bigger than 10. So go back to the equation. I'm going to do 11 because it's bigger than 10 and still not huge. Plus 80 times 11 plus 11 squared. All of that divided by 11 is 545, which is less than 590. So this section is true. And then we need to pick one bigger than 500. So we'll do it one more time. 5,000 plus 80 times, I'll just do like 600. 600 squared divided by 600 is 688. So it's bigger than this, so it would be false. You can't always look at a problem and know that it's going to alternate false, true, false. So you have to check them all. Don't skip steps. All right, where is it true? It's true between 10 and 500, including the endpoints, because this one was or equal to. So the final answer on this problem is between 10 and 500. This is the algebra. But for this problem, it was in hundreds, I believe, if we read the question. Where is it? Oh, sorry. Number of hundreds of units produced. So we just have to stick hundreds on our answer. So add 2 zeros. 2 zeros. So between 1,000 and 50,000 TVs for the context of this problem. And that concludes lesson 6.6. So finish all of your chapter 6 homework and turn that in as soon as you get it done. I'll be posting the answers to that after the due date.